Hello, students. Welcome to Chapter 3 in Neurobiology. This is a chapter all about neurons and how they send messages. We won't get too much into depth about the actual synapses until we get further into the chapter on pharmacology, but this will give the basic information of how neurons work. So again, there is a bunch of videos right here. Most of these we're going to go through in the lecture. A few of them we don't. There's a couple different clips, so if you want another couple visual examples of the things we talk about in this chapter, go through here, but we will watch a few of these here in the lecture recording. So, quick review of a couple of the key pieces that I want you to be aware of as we're going through this chapter. One is the main ideas behind the nervous system. So, some of the big pieces that I want you to understand the concepts of are plasticity and integration. Plasticity, as we've talked about, is that capacity for change and modification. I think of it like a piece of rubber that can bend or a piece of plastic that can bend. It can change, it can move. And that really is coming because of the physical properties of neurons, them connecting to other neurons, how they work themselves, how they strengthen connections between neurons. And we won't get a ton of depth, but understanding some of the basic processes there, I think will really help you as we go through the rest of the course, talking about neural substrates of different things in our brains. So integration is the idea that we're using a ton of our brain, a ton of different components or pieces or parts of the brain. So if you remember chapter 2 and all the different areas focused on different things, well, they're all integrated. They're all working together. So your sight, the sounds, the touch of things, your balance, the smells, messages from your organs, and everything that's going around in your current thoughts, they're being integrated all throughout the brain. A lot of those processes are not necessarily conscious, and a lot of those things are happening in the background with so many different nodes connecting in our brain, systems of neurons, networks of neurons all throughout the brain, integrating to our experience, to what we decide to do, all these kinds of things. So that plasticity and integration are two really big pieces to be aware of as we go into the chapter. Also, things making memories, making meaning, making connections. So, also the nerves themselves, afferent nerves are carrying information in or up towards the middle of the brain. So, that is things like your sensory nerves, and then efferent nerves are carrying messages out. But again, these are still neurons. So, if you've read the chapter before watching this lecture video, which I hope you did, you will see this neuron here, and it's got some special sensors. And then you can see some dendrites of this neuron here, and then its axon talking to a muscle cell. So here is a neuron. There are many specialized neurons in the body, and we'll talk about a couple of them in a little bit of detail, but all of them share these characteristics. These are some key components of a neuron. You've got a cell body here, just like other cells in your body. The cell body has the nucleus in here. It has all of your chromosomes, all the DNA, just like any other cell in your body. And so the cell body is doing things, well, I've got a slide on that in a moment. Another big thing is the axon. So neurons have this single axon, and it is usually the thing that is myelinated with this myelin sheath, and we'll get a little more detail on that, helping speed up the transmission, but that is where the message goes out. Another big part of it is the dendrites. So this is where the message comes in. So all neurons have, some have a little bit of specialized sensors for like light in your eyes, for example, in your retina, but they have these components. They have a receiving end, they've got the nucleus and cell body and axon to send the message, and then it will end in these axon branches. So again, a neuron has only one axon, but it can have many branches down here at the end, talking to lots of different neurons. All right, so the cell body, again, like I said, has the nucleus. It's directing the growth, the maintenance of the cell. It is just like any other nucleus and any other cell body. It's maintaining the health of a cell. And that's a really important thing to think about when we are remembering plasticity. So neurons are a living bit of your body, a living cell. And just like other cells, they need things like energy. They need things like oxygen. They need these components to run. And so some of the things that we do, whether it be drugs or having less oxygen or less sleep, we can put strain on the individual cells. So some of the things that we see going forward will come from strain on the neurons themselves. Some of it will be because problems or trauma to the neurons themselves. Like if you break an axon, well, where's that message going to go? It can't go down to these synapses anymore. So with this, just remember that a neuron is a cell. It wants to be efficient. It does its job, but it's trying to be efficient, and they use a lot of energy in our brain. So we've talked about this before, but neurons do use a lot of energy overall to do their processes, and so they try to be as efficient as possible. And that's a big thing with plasticity. That's a big thing with building and breaking habits as well, is that it tries to make networks really efficient. And so it can be hard to break those, say, habits of something that you don't want to do because it's now a really easy, efficient path for it to take. All right, so the axon is carrying information away from the cells. In humans, they can be up to 3 feet long, all the way down your spinal cord. And neurons can have only one axon, but they can have many branches at the end. So they can talk to thousands of other neurons from their one axon. So dendrites, you can think of them as the receiving piece. They're receiving information from other cells around, and then they send it either across the cell body to the axon, and then most neurons have many dendrites. It's easy for it to, well, it can create axon branches, not new axons, but it can make new axon branches, and it can make new dendrites. But again, a big piece of that is that takes energy, that takes resources. To maintain this dendrite, you have to have nutrients, you have to have energy to maintain that. And so if you're not using that dendrite, you might reabsorb it or kind of just lose it because it's not being used. So it's not getting it's not getting energy, and so it kind of just falls off, or it just gets reabsorbed and reused and recycled. So with that, that is part of plasticity. These axon branches growing and the dendrites growing are a big part of plasticity. If they are being used, they're going to stay there. If they're not being used, it's kind of like a tree. You're pruning a branch on a tree. That's why we call it pruning. So it literally cuts off that branch of an axon. So down here, if you're not using that one, you can cut that off. You can cut off that dendrite, and that helps the cell be more efficient. If it's not using it enough, it's not going to keep that maintained. But again, these dendrites and any given neuron can be connected to thousands of other neurons. Then the myelin sheath, we'll talk a lot about the physical processes of how this happens, but essentially this is fat cells that insulate the axon. Other cells around it, glial cells, make the myelin sheath and wrap the neuron, the axon, with it. And that helps speed up the transmission speed. And we'll talk about that as we get to the actual process of how transmission happens. But that's an example of one of the neural substrates of one of the disorders that we look at is multiple sclerosis. That is a hard one to say, even though I'm pretty familiar with saying that one. So family members with multiple sclerosis. So it is hard to say fast though. But with that, that's from damage to myelin, hardening of myelin. So that is one little hint for things to come later on in the chapters. All right, so here is another picture of a neuron and then an other neuron that it's talking to. So here we see a nucleus in the cell body or the soma of the neuron. We see a long axon right here with some axon branches. It has a synapse. Maybe these ones are connected to other neurons that are out of the picture. Here's a bunch of dendrites that are receiving messages from other neurons. And then you can see the myelin around this axon. And then on this one, you see dendrites, cell body, and axon. So one thing that I want to show you is a pretty cool thing. This will come up later on in the chapter or in the class. If I'm not wrong, I think it's chapter 7, which I might be wrong, but we'll talk about the development of the brain in more detail. But one thing I wanted to let you know is how quickly neurons can develop and grow. So a human stem cell is the thing that becomes neurons. That is another critical piece of plasticity and the limits to our brain, is that these neurons, they do not divide to become new neurons. So no neurons divide to become new neurons. That would be great if they did. Things would probably be very different for us if that happened. But what does happen is human stem cells do divide, and some of those can become neurons. So we have in our brain a couple specific places where we have human stem cells still active and creating new neurons: hippocampus, olfactory bulb. Um, how much it actually impacts our thinking, well, that's for hybrid activities in later chapters as well. But that is how we get new neurons. So this is happening a ton early on in life. So when you are prenatal, that's essentially a big part of what's happening prenatally, is there are stem cells and they change into a neuron, they migrate to where they're going to live, and that's where they live. And so that is happening a little bit. It slows down dramatically after the age of 2. It almost stops. So kind of almost effectively stops at about age 2, but it's still kind of happening and slowing down. But the dramatic difference of growing a brain up to age 2, and then the rest of your life, it's almost like it stops completely. But let's watch a video of a human stem cell becoming a neuron. And this whole process takes a few days or can take a couple days. And so pay attention to like how quickly the morphology changes of these cells happen with the hour timer in the corner. So I'll pause it there really quickly. I'm not sure if you can see my face or not, but essentially here is a, essentially a petri dish of human stem cells, and essentially you put this neurogenic cell medium, basically a chemical, so a chemical process that's naturally in the brain. They put that directly into these stem cells and they stop dividing. But again, that's how we get neurons. It's stem cells divide. Once this neurogenic cell medium tells them to stop dividing, it also is telling them start becoming a neuron. So essentially what this is saying is that some of the cells have trouble actually getting all the way to a neuron. So it's showing that there are some cells that aren't quite making it all the way to neuron. They're having some trouble. Versus this is a comparison of cells that are doing it well. They're getting all the way to neuron is what's happening here. So here you can probably see we've got a cell body. You can tell these are probably dendrites there, an axon right there, as well as in the previous version, you saw some of the components kind of being reabsorbed as this becomes an axon and some dendrites around there. But a key part of that is how quickly these changes happen. And a key part of that, of looking at this hours of how quickly this happens, is Neurons, even as neurons after they've been neurons for years, can grow those axon branches, those dendrites pretty quickly. So within hours. So like over the time you're sleeping, you can be growing new axon branches, you can be growing new dendrites. So hopefully you found that interesting. I really like that video. You can think of human stem cells as a blank slate cell. A stem cell can become a bone cell, it can become a muscle cell, it can become a brain cell. That's what a stem cell is. It's kind of a default state cell, like a putty state. It can become what it wants to become based on other chemical reactions that are happening in your body. And there's a lot of complexity that goes into that we won't get into. Our main focus of looking at that is to see really how quickly that is. Because these dendrites, these axon branches, they can grow pretty quickly. Like I mentioned, just overnight, after you are learning something new, you're probably starting to either make some stronger connections, or you might even be making some new branches to reach out to other neurons. So here is the synapse. This is when you get to the end of the axon branch. Here we've got the end of that axon branch and we've got the dendrite. It's a postsynaptic spine on a dendrite of the next neuron in the pathway. And the synapse is this space between neurons. It is that site of communication. Neurotransmitters themselves are the chemical messengers. They bind to receptors on the next dendrite, and that starts the action potential. And we'll get more into detail on neurotransmitters. We will get a little bit more detail today, but most of that will come in the chapter on psychopharmacology because it's so directly related to a lot of the different drugs that we use. Usually the drugs are trying to keep these neurotransmitters in that area, pretend to be the neurotransmitters, make them be sucked up or reuptaked quickly. That's what most of the medicines that we have do, and that's what some recreational drugs do as well. So the receptors have basically little proteins that are on the cell surface, and they're different shapes. They connect to a different chemical, and when that neurotransmitter attaches to it, it helps start a action potential in the next cell. Reuptake is that kind of vacuuming up. It's taking the neurotransmitter back up into the previous neuron. Another thing that can happen if it's just hanging out there, glial cells can like break it down and recycle it that way too. Kind of throw it away. So the next thing I want to talk about is the neural impulse. How do we actually get a message down that axon? I think this visual example is really good, and then we'll probably watch a little bit of this one just to make sure and kind of drive the point home. But hopefully with this video, and I'll probably interrupt it a couple times to point out a few things, you'll be able to tell how a neuron sends a message all the way down that axon.
How does the pain you experience when you burn your hand result so quickly in an action by your muscles? Many animals respond to environmental stimuli using specialized cells called neurons. A stimulus is detected by sensory receptors, and the body responds through motor effectors.
So really quickly, you might not have noticed, but we talked about this in class, that in your spinal cord, it can make decisions for something like this. As it's getting to your brain, here the spinal cord said, hey, pull the arm back, activate muscles to pull the arm back. So just one little quick thing that you might have missed.
Detected by sensory receptors, and the body responds through motor effectors. These cells working together allow you to respond very quickly to threats. When you touch something hot, heat receptors of a sensory neuron detect the stimuli and send the information of heat to an interneuron in your central nervous system. From there, a motor neuron sends a response from your central nervous system to the skeletal muscles in your arm.
So, quick interruption again. You can see here a couple of the different types of neurons. So you can see the interneuron are things that are in your spinal cord, they are in your brain, and so that's what a lot of our neurons are. And then we've got sensory neurons. You've got different sensory neurons in your eyes. You have what are called hair cells in your ears, and you've got a bunch of different senses for your skin. And then motor neurons, basically here at the end, instead of spitting out all sorts of neurotransmitters, motor neurons basically spit out chemicals like salt that can activate muscles. This is actually one reason if you like fillet a really fresh fish and like pour salt on it, the muscles might contract because the muscle cells are actually getting um, activated because of that sodium. It's an interesting connection.
causing them to contract and pull your hand away. The fundamental process of neural transmission that underlies this action occurs in all neurons of the body. Neurons transmit.
Okay, with this picture, this is a really good visualization, but I want to make sure you understand what's going on here. So here is the outside of the axon. So brain soup, you can see other neurons back there. You can see some chemicals over here. So this is the outside of the axon. This is the membrane. This is the upper membrane. We've kind of split the axon in half, and this is the inside of the axon. So a little bit below the screen, we would have another membrane that looks just like this, that also has these voltage gates. So here we've got inside of axon. Below the screen, we also have another membrane that looks like this, and this is the upper membrane of that axon, and here is the outside of the cell. So inside of axon, outside of axon, and this is the membrane.
This information through changes in the electrical potential of the membrane by the movement of ions across the membrane. An electrochemical gradient governs the movement of these ions, resulting in an electrical impulse. The resting membrane potential in a neuron, when the cell is not firing an impulse, is established by the unequal distribution of sodium ions outside of the cell and potassium ions inside the cell, making the outside of the cell more positively charged compared to the inside. The electrochemical
So just another way to say that, it is pumping out 3 sodium ions and it's pumping in 2 sodium ions at a time. This means that there is a slight negative charge inside the axon versus outside the axon. With that being said, this charge comes from just simple molecules. An ion is just a charged particle, one single molecule that has a slight positive charge. These ones also have a slight positive charge, but there's more positive out here. So comparatively, this is more positive than in here.
gradient is established and maintained by an enzyme called sodium-potassium ATPase. When a neuron is stimulated, sodium ion channels open and sodium ions flow into the cell. This leads to a change in the electrical potential across the membrane called depolarization. The depolarizing electrical potential travels down the dendrites and over the cell body. Multiple electrical potentials will combine at the axon hillock in a process called summation. If the depolarization is large enough, an action potential is triggered. Action potentials are all or none electrical impulses that maintain their amplitude and strength down the length of the axon. The action potential travels down.
So before it continues, I want to make sure this is clear. It has this little glowing light, and it can be a little deceptive because, again, this is just the membrane. So the actual charge is not just traveling along the membrane. So here is the inside. The charge is because of the movement of the ions back and forth. So the charge is like a wave. So you get this area is more positively charged, and now this area becomes positively charged inside the axon. Then this edge section becomes more positively charged. Then this section becomes more positively charged because of these voltage-gated channels letting in and out the different ions that are part of it. So it's a little misleading to see this kind of glowing. It's really just a matter of ions moving back and forth in a wave, in a pattern, to make this area becomes more positive, then this area becomes more positive, then this area becomes more positive, all the way down the axon. That's how it keeps its same strength the whole way down. It doesn't degrade because it's just these ions moving back and forth in a wave pattern.
The axon, when the depolarization of an area of membrane causes adjacent voltage-gated sodium ion channels to open. The influx of sodium ions results in membrane depolarization along the membrane. After a short delay, potassium ion channels open and potassium ions flow out, repolarizing the membrane. For the neuron to fire again, the resting membrane potential needs to be re-established. Sodium-potassium ATPase is used to move sodium and potassium ions against their concentration gradients, re-establishing the resting membrane potential.
So the main idea there is it takes energy to pump those ions back out so that this stays negative on the inside. And here we've got a better visual of the whole axon. So this is the upper membrane, this is the lower membrane, this is outside of the axon, this is outside of the axon, some of that brain soup back there. So we can see a negative charge, and you'll basically see a wave traveling down the axon with a little section of positive charge all the way down.
As the action potential moves down the axon, ions are diffusing only a short distance, allowing the signal to move quickly. At the axon terminal, the electrical impulse passes to another cell at a cellular connection called a synapse. The space between the presynaptic neuron and a postsynaptic cell is called the synaptic cleft. The presynaptic neuron contains signal molecules called neurotransmitters that are packaged inside vesicles. When an action potential reaches the end of a neuron, neurotransmitters are released by exocytosis from the neuron into the synaptic cleft. Neurotransmitters bind to the adjacent cell at receptor sites attached to ion channels. The channels open, allowing the movement of ions into or out of the effector cell, which alters its membrane potential, thereby transmitting the signal from the neuron to the effector cell. Because nerve impulses move very rapidly down the axon of a neuron and move from cell to cell across synapses, you react quickly to a stimulus, like burning your finger.
All right, let's watch one other video that I think just gives a different visualization of it, but it's the same basic content.
A nerve impulse is an electrical current that travels along dendrites or axons due to ions moving through voltage-gated channels in the neuron's plasma membrane. Voltage-gated channels open and close in response to an electrical voltage, so they are affected by changes in electrical charge around them. When a neuron is at rest, a charge difference is maintained between the inside and outside of the cell. This charge difference is produced and maintained largely by active transport using sodium-potassium pumps. The pumps send sodium ions out of the cell and bring potassium ions in. While other channels allow some flow of potassium ions back out of the cell, the sodium ions cannot easily get back in to replace the lost positive charges. The overall result is that the exterior of the cell has a net positive charge and the interior has a net negative charge. The difference in charge between the interior and exterior of the cell is called the resting membrane potential. A nerve impulse begins when a stimulus disturbs the plasma membrane on a dendrite, causing sodium channels to open. Sodium ions flow into the cell, lessening the charge difference at that location. If the change is enough, it will cause nearby voltage-gated sodium channels to open. This allows so many sodium ions to flood into the cell at that location that the membrane there is depolarized, with the local region inside the cell having a net positive charge and the outside of the cell having a net negative charge. This affects neighboring voltage-gated sodium channels, which then open, moving the depolarization along the membrane. This moving depolarization is called an action potential. Changes occur behind the action potential to restore the resting membrane potential. The voltage-gated sodium channels close and voltage-gated potassium channels open. This allows a rapid flow of potassium ions out of the cell, repolarizing the membrane so that the inside is again negative and the outside positive. This is followed by use of sodium-potassium pumps to fully restore the resting membrane potential and to reestablish proper concentrations of sodium and potassium ions inside and outside the cell.
All right, I want to pause it right there. So hopefully this image, we've got the outside of an axon and outside of the axon, or a dendrite, honestly. But the outside, and then this is the inside. So here's the membrane, the upper membrane. Here's the lower membrane. We've just sliced it in half. And we can see inside, we see those ions just moving back and forth across the membrane. So it moves here, moves back, moves here, moves back, moves here, moves back. That is how neurons send a charge down, because as it moves here and makes it more positive, that makes this area then open up and an ion comes down, makes this more positive, that makes an ion in here go more positive, positive, positive in a wave across, and then they go back out. So these ions are only moving just across that membrane. There's no ions shooting all the way down the axon. It's not sending a lightning bolt. It's not sending an atom. It's not sending anything all the way down. It is a wave of changing charges all the way along the axon. So hopefully this visualization helps that be more clear. I'll kind of rewind and rewatch this part of it in that wave. And if you have me in an in-person class, we'll do the wave in class because it's kind of fun. We can all see how quickly we can do the wave as our neurons in our brains are trying to help us move. Well, those videos have the process happening pretty slowly overall. We'll talk about the speed of it in a second as we kind of review it, but I want to talk about the types of neurons really quickly. So the sensory neurons are those ones that are taking information from the world around us. Motor neurons are sending out messages to muscles to move, and then interneurons are most often what we're talking about in the class. They're the ones that are in your brain. They are the ones that are in your spinal cord. They're how we are processing sensory input, planning things, deciding to act, those kinds of things. Most of what we're going to talk about most of the time in the class are interneurons, but sensory and motor play a big part of that too. Another one is, this was talked about in your book, unipolar, bipolar, and multipolar neurons. Here we see a couple examples, a little bit different, a little bit distinct, but some of the same components. So we have different combinations of dendrites and axons, things like that. Another big thing here that we don't touch on too much, but there's a lot more recent research on glia cells that show that they're a much bigger part of the whole picture of what your brain is doing than we previously thought. So here you can see in green, there is a neuron. You can see a bunch of other cells in red here. Those are glia cells. So those are other brain cells that do other things. So glia cells, we used to think that they were literally just a scaffolding, like that they kind of were a framework that neurons could, as they went from a stem cell to become a neuron. They used their kind of viney appendages of dendrites and axon branches to move and be where they were going to be. So they kind of just held it in place like you would a scaffolding of a building is kind of holding people in place as they're building it. They thought that glia cells were, that's kind of what they did. But now we see, oh, glial cells are actually what create the myelin insulation. They literally wrap axons and insulate them. They also do a lot of bringing nutrients to neurons and taking waste away from neurons. They also do some communication support. So there's conflicting evidence of how much this is involved in the process, but it does seem like some glia cells can create neurotransmitters to then be used by nearby neurons. So they are a bigger piece than we used to think. So neurons are usually what we focus on. Maybe 10 years in the future, we'll have some cool breakthroughs and we'll have a bigger section on glial cells, but that is what we know for right now, at your level anyway, that we'll talk about. And the neurons are the main focus. They're what we're going to be talking about as sending the messages back and forth all around the brain. So the resting membrane potential, we've talked about this before, but our brain uses about 20% of our whole body's energy. So it's a pretty small organ comparatively to the rest of your body, but it uses about 20% of your energy. About 15% of that energy is just maintaining a resting membrane potential. So this is from a fairly recent study. I've got a link to it in the slide notes if you want to look at it in more detail. But essentially, it's showing here that, well, housekeeping things, that's things like getting energy, getting food, that kind of stuff. But this is RP is resting membrane potential, AP is action potential, and then the energy of managing the synapses is a big part of that. So reuptaking things, spitting things back out, that takes a lot of energy. But the resting membrane potential takes about 15% of our neurons' energy. So just being ready to fire is taking about 3% of your total energy every day. Just having like the neurons ready, like having that slight difference in charge, being a little bit negative inside, a little bit positive outside. That is taking about 3% of your total energy every single day just to do that. And it's even while you're asleep. Doing that. It takes a little less energy while you're asleep because it's not having to do some of the other things. So the brain is using a little less than 20% when you are asleep. But it's pretty neat, I think. So as a reminder, those ions are those electrically charged molecules. They are in a fluid in the brain. It's pretty similar to salt water. There's chemicals in there. Sodium is the Na plus, potassium is the K plus, chloride is here, and then there's other negatively charged particles. Your book just calls them anions. So there are other chemicals there, but the main ones we usually are talking about are the sodium and the potassium there. And again, they are only moving that small distance across the membrane. So ion channels like the sodium-potassium pump allow ions to go through that membrane. These pumps use energy to keep that slight negative charge. So here is a much more detailed video than the ones that we've already covered. I think it's a really good one to watch, especially if you're still confused. It puts these things together with some of the other things that you've read in your book. So we will watch this video as well, just from about 3:18 to 8:30 in the video. But again, it's the main idea is I want you to understand that this process is a wave of these axons going back and forth just a little ways. So the charge is waving or a chain reactioning all the way down an axon till it gets to the axon, the end of the axon branch, to that terminal at the synapse, and then sends that message to the next dendrite in line. So we'll watch this video as well. And hopefully that gives you a lot of visual examples of how this process works. Because that process of getting a message from the dendrite all the way to the axon branch, it's a really key piece of our thinking, our processing, the energy that it's using, the nutrients you need for your brain, the myelin sheath. It's a core component of a lot of the neural substrates that we're going to talk about later on.
Something useful. Okay, now that we got Electricity 101 down, let's see how it works inside your nervous system. A resting neuron is like a battery just sitting in that sack that is you. When it's just sitting there, it's more negative on the inside of the cell relative to the extracellular space around it. The difference is known as the neuron's resting membrane potential, and it sits at around negative 70 millivolts. Where do those charges come from? Outside of a resting neuron, there's a bunch of positive sodium ions floating around, just lingering outside the membrane. Inside, the neuron holds potassium ions that are positive as well, but they're mingled with bigger negatively charged proteins. And since there are more sodium ions outside than there are potassium ions inside, the cell's interior has an overall negative charge. When a neuron has a negative membrane potential like this, it is said to be polarized. Now, these ions didn't just show up in this arrangement on their own. This is all orchestrated by one of the most important bits of machinery in your nervous system, the sodium-potassium pump. This little protein straddles the membrane of the neuron, and there are tons of of them all along the axon. For every 2 potassium ions it pumps into the cell, it pumps out 3 sodium ions. This creates a difference in the concentration of sodium and potassium, and a difference in charges, making it more positive outside the neuron. This difference is an electrochemical gradient, and you probably know enough about biology by now to know that nature hates gradients. It wants to even out all of those inequalities in concentration and in charge to restore balance. But the only way to even out that gradient is for the ions to pass across the membrane. Thankfully, the sodium-potassium pump isn't the only way in or out of the cell. The membrane is also riddled with ion channels, large proteins that can provide safe passage across the membrane when their respective gates are open. And these gates open and close for different reasons depending on their structure and purpose. Most are voltage-gated channels, which open at certain membrane potentials and close at others. For example, sodium channels in your neurons like to open around -55 millivolts. But some others are ligand-gated channels. They only open up when a specific neurotransmitter, like serotonin or a hormone, latches onto it. Then we also have mechanically gated channels, which open in response to physically stretching the membrane. In any case, when the gates do open, ions quickly diffuse across that membrane down their electrochemical gradient, evening out the concentrations and running away from other positively charged ions. This movement of ions is the key to all electrical events in neurons, and thus is the force behind every single thing we think, do, and feel. Of course, not all of your body's electrical responses are the same, and neither are the flows of ions going in and out of your neurons. If only a few channels open and only a bit of sodium enters the cell, that causes just a little change in the membrane potential in a localized part of the cell. This is called a graded potential. But in order to send long-distance signals all the way along an axon, you need a bigger change, one big enough to trigger those voltage-gated channels. That is an action potential. And your best bet for making that happen is to depolarize that resting neuron. I mean, cause a big enough change in its membrane potential that it'll trigger the voltage-gated channels to open. It all starts with your neuron sitting there at resting state. All of the ion channels are closed and the inner voltage is resting at -70 millivolts. And then something happens. Some environmental stimulus occurs, say like a spider brushes up against a tiny hair on your knee, triggering those sodium channels to open, increasing the charge inside the membrane. Now, the stimulus and the resulting change have to be strong enough to cross a threshold for the true action potential to kick in, and that threshold is about -55 millivolts. Remember that number, because this is an all-or-nothing phenomenon. If the stimulus is too weak and the change doesn't hit that level, it's like a false alarm. The neuron just returns to its resting state. But kind of like Doc Brown hitting 1.21 gigawatts in the DeLorean, once it hits that threshold, you're not going to travel in time, but you are going to see some serious action potential. At that threshold, the voltage-gated sodium channels open, and there are
So just to make it clear, the basic process here is if there is enough change in the charge, the voltage-gated channels will open. That's just how they work. And so if they open, it makes the inside of the cell become more positive relative to the outside of the cell, and that is how that action potential stays in its strong form all the way down the axon. Because again, this is here the inside of the axon, this is outside of the axon. It's not shooting ions all the way down. It's just moving them across this membrane. And that's also how it can be so fast and so consistent across our whole brain, because it's really just down to these little chemical processes. They're very complex processes, but hopefully this is helping you understand what is actually happening at the molecular level.
tons of these, so all of the positive sodium ions rush in, making the cell massively depolarized. So much so that it actually goes positive, up to about positive 40 millivolts. This is action potential in action. It's really just a temporary reversal of a membrane potential, a brief depolarization caused by changes in currents. And unlike graded potentials, which are small and localized, an action potential kicks off a biological chain reaction which sends that electrical signal down the axon. Because each of your neurons has lots of voltage-gated sodium channels, so when a few in one area open, that local current is strong enough to change the voltage around them, and that triggers their neighbors, which triggers the voltage around them, and so on down the line. As soon as all that's underway, the process of repolarization kicks in. This time the voltage-gated potassium ion channels open up, letting those potassium ions flow out in an attempt to rebalance the charges. If anything, it goes too far at first, and the membrane briefly goes through hyperpolarization. Its voltage drops to -75 or so millivolts, millivolts before all of the gates close and the sodium-potassium pumps take over and bring things back to their resting level. Now, when part of an axon is in the middle of all this and its ion channels are open, it can't respond to any other stimulus, no matter how strong. This is called the refractory period, and it's there to help prevent signals from traveling in both directions down the axon at once. So that is the surprisingly simple app that your nervous system uses to let you experience the world. And because the voltages in this process are always pretty much the same, the initial threshold around negative 55 millivolts and the peak depolarization at 40 millivolts, your neurons only communicate in a single monotone buzz. It doesn't matter if it's a spider on your knee or an elephant.
The rest of the video is pretty good and goes into a little bit more detail. And there's another video that I think I have linked about what happens at the synapse. But yeah, that's a good place to stop there. Hopefully you have a really clear idea of what is happening in this neural communication, what the action potential actually means. It is that charge traveling down the axon. When it gets to the end, it spits out some neurotransmitters. But again, this is caused by the movement of the sodium and potassium going just across the membrane in that pattern. So the book gives a really good example of summation, which was talked about in that video. Essentially, the idea is you have to have enough of a change to a positive charge inside to have an action potential start. So there is a game that I used to play, as well as the authors used to play, in gym class where we would have a giant parachute. You would try to use the parachute to push a ball to the other side. And if you had competing messages coming in, you might not be able to get that ball across. So here we're going to watch I might just pull up the video and not actually watch. These kids, they're using this. You can do different things like try to make a ball roll around. You can try to have one side throw a ball to the other side. Can try to get it to like the hole in the middle. You can make it a big circle around you. That was always really fun. The idea here is that summation is the different messages coming into the cell body or the dendrites, and then if there is enough of them, if they get the right amount, then it will start the action potential. So again, you need summation. You need enough of this positive change to open up those voltage-gated channels to let this pattern of sodium and potassium ions going back and forth, let that message go down in a wave. So again, as was mentioned in the video, there can be, after that action potential, you go a little bit negative as they try to balance themselves back out. And here is when the red is if summation is not working, if you're not getting enough of a message, if it's not getting past this point, but if it gets past that point, other voltage-gated channels open, and you get the Na plus to move inside and get the sodium to move inside, becoming more positives. So this whole process of sending that signal, so of these ions just going back and forth, oops, too far. So this process of going just back and forth across the membrane lets neurons fire, in humans anyway, anytime as much as 10 to 200 times per second. So in some cells, it's faster, or in some parts of our brain, it's faster. In some parts of our brain, it's a little bit slower. But about 10 times a second is the slowest. About 200 times a second is the fastest. We've measured that they could potentially go faster than that, but it seems like these are about the points, the range that our brain is operating on. So your sight refresh rate is 200 times a second. So the whole processing and deciding what to do is going to be a little bit slower than that. But if you've ever, say, tried to watch a movie on a really high refresh screen, so something like 60 hertz is changing the image 60 times a second. Something that's 120 is changing 120 times a second. If you have something that is higher than 200, it is changing the screen faster than your neurons are doing that. So you are actually refreshing your eyes. Your visual perception is refreshing at about 200 times a second. Also, different parts of your brain are working at these different speeds. So the average speed is closer to the 10 times or 10 10 refreshes per second because you're using different parts. Remember that integration, we're using lots of parts of our brain, so we're getting that sight and getting that pretty quickly. The neuron can send that message. Again, the sodium, potassium coming in and out, sending that wave of electrons down 10 times a second to 200 times a second. It is very, very fast, very efficient to be able to get that cycle of just moving. It would be much slower if you were trying to shoot an ion down a 3-foot axon, but because of this process of action potential and it's just moving those little molecules back and forth, this can happen much quicker. So the overall speed of your brain is somewhere there. If you're thinking about something really hard, you're thinking somewhere the in the range of between 10 and 200 bits per second, which is pretty quick, quick enough to do the things that we do, but maybe a little slower than you might have thought. Myelin is a really important component of this whole neuron and brain process. The main ideas to take from this is that the myelin speeds up that wave of electrical current in an action potential. So it lets all the neurons that are myelinated talk faster, so that speed of going all the way down the axon, it's kind of giving it a quicker boost. So myelin itself is actually the glial cells. So here we see an example here, and I don't know how to pronounce it, but I've read it. That's how it's spelled. So that's this type of cell makes the glia cell, or makes the myelin. It wraps itself around the axon in a couple segments along it, and that doesn't let any fluid, that doesn't let any of the molecules. It's basically right against that membrane. And so that means there are these little bits where there is not myelin. So those are called nodes of Ranvier. And essentially what that means is as there is the depolarization in the axon, rather than having to send that wave all the way along this whole axon, it kind of jumps. There is a little bit of degradation, right? Because you're getting this space positively charged, but because the axon potential is such a dramatic change in the charge, that positive charge, it can jump this a little bit. Remember, these are very small spaces we're talking about. So this is at the cellular and molecular level. So it does degrade a little bit, but not enough that it's stopping the communication in that neuron. So essentially, the message is kind of skipping a section. So it's basically jumping between those nodes of Ranvier. So, and then it gets to the axon terminal, spits out some neurotransmitters. So there is a really good video from Crash Course that's a follow-up to the other one we've watched part of, and it is linked in your slides, but we're going to watch that in the chapter on psychopharmacology to talk more specifically about what happens at the neurotransmitter level. But essentially, we've got that wave of the wave of positive charge that usually goes down like this. Rather than going down in a slower pathway, it's doing quicker jumps, which speeds up the communication, makes it so your whole brain processes a little bit faster. And that myelination basically starts from the oldest parts of the brain, so back here at the brainstem, and kind of goes in this pattern up towards the front. So about the time of adolescence, the emotion centers of your brain, so like the amygdala, those are being fully myelinated. And then by the time you are in your about 22, 23, definitely by 25, because again, it's a range. So just it's not going to be an exact month, but there's a range. So sometime in your early 20s, the rest, your prefrontal cortex gets finished up myelinating. And that's not to say there's no myelin there. So there is, your whole brain's kind of doing it at once, but it kind of focuses on this sort of pattern. And so by the time you are in your early 20s, that's finished myelinating. And that's really what people mean that's where the idea that your brain doesn't finish forming until you're in your 20s comes from. The cells that are there are pretty much there by the time you are two. There's, like we mentioned earlier in this lecture, there's very little stem cells becoming neurons in human brains. And so pretty much you've got all the components there at the time you are two. The big changes are one, making new connections that are more relevant to the things that you're doing or keeping those connections strong, losing or changing with the plasticity. And another is that myelin. The myelin can make things happen faster. So adolescents are literally feeling emotions stronger and bigger. It's using that center of the brain. The brain likes to be efficient again. So it's going to use those myelinated areas a little bit more. That's being said, you can use the prefrontal cortex. An adolescent can use their prefrontal cortex. It takes a little bit more energy. It takes a little more effort for them to pull that into the neural network, but they absolutely can. They're definitely capable of that. And we can see that in looking at adolescent development, all the really amazing things that adolescents are capable of. So it's a little bit dismissive and a little incorrect to say that the brain finishes developing. It's a little bit true, but it's usually used incorrectly because, yeah, it's not finished myelinating till you're in your 20s, but that doesn't mean you can't do the same things as, say, an adult brain. So you can learn those things. You can teach a young human new tricks. You can teach an old human new tricks as well. All right, with this, this is a good little visual of how this myelin works and in dominoes. So the dominoes that fall down, and it kind of gives you a little visual example of how that works and jumping between those nodes of Ranvier.
The body's information system is built from billions of interconnected cells called neurons. A nerve cell or a neuron consists of many different parts. The cell body or soma is the life support center of the neuron. The dendrites are branching extensions at the cell body. They receive messages from other neurons. The axon is a single extension of a neuron which is covered with myelin sheath to insulate and speed up messages through neurons. The terminal branches of axon are endings that transmit messages to other neurons. Action potential is a neural impulse. It is a brief electrical charge that travels down an axon and is generated by the movement of positively charged atoms in and out of channels in the axon's membrane. The propagation of a nerve impulse down an axon can be modeled by a row of falling dominoes. Resting potential is the state when no impulse travels along the neuron. All or none response. This is illustrated by the fact that the push on the first domino has to be strong enough to knock it down. Pushing harder, however, does not affect the impulse's speed. This shows how the action potential affects one area of the axon at a time and is sequentially passed on from one section to the next. The dominoes can also be used to demonstrate that more than one action potential can be traveling along the axon at the same time. Dominoes lying on the table illustrate the neuron's refractory period. The axon is not immediately able to convey a new action potential. Forming a domino line that branches out illustrates axon collaterals, in which the action potential affects all the branches equally. The dominoes can also be used to demonstrate how myelination increases the speed of transmission. The action potential travels faster if it can jump from node to node rather than having to pass on sequentially. This is called saltatory conduction, and the nodes are called the nodes of Ranvier. When one of the channels in the axon's membrane becomes dysfunctional, it could have serious effects, as in the case of multiple sclerosis, in which myelin sheets around axons of the brain and spinal cord are damaged.
I like that animation of seeing the ion go back and forth across the membrane. So hopefully that helps make that more concrete for you. But also seeing the dominoes fall at the different rates. So if you've got the dominoes at the nodes, and that the myelin is that connection between them. So it has to jump across that connection. Really, it's inside. It's not over. It's inside. Your book also has a diagram where it's like a spinning axon and there's electricity on the outside. again, it's not a lightning bolt. It's not going around the outside. The molecules, the ions, are going back and forth across the membrane. And so it's gone back and forth, and there's enough of a positive charge at the next node, the gates open, and it continues that message. So it's jumping across on the inside because of that just movement across the membrane. So this is a good video to kind of sum up a lot of the neurotransmitter talk that we've gone over. It's a good little animation. So honestly, if you want to skip this, if you're like, oh yeah, I'm really clear. I've already watched, I don't know, what have we watched now? 4 videos about this process. So if you want to skip it, that's okay, but it is a good one putting a lot of these pieces together. So hopefully watching that video did help your understanding, seeing them work together. But again, this is happening very quickly. A single neuron can again send 10 messages a second to up to 200 messages a second, depending on which part of the brain it is in. And so that's happening all throughout. So neurons from the back of your brain, talking to the front, talking to the motor cortex, everywhere around. And that's the integration that we talked about at the very beginning of this chapter. So a little bit about neurotransmitters. This is very brief. This goes a little beyond your book here, and we'll come back to this in a little more detail when we get into the chapter on psychopharmacology, but just a little detail here before we get to that in another week. So a neurotransmitter is essentially just a chemical messenger. It is literally a molecule, and there's over 100 specific neurotransmitters in human brains. And they have 3 primary jobs. So we'll break up these 100 specific neurotransmitters with slightly different molecular makeup into more simple terms. So the 3 main jobs are excitatory, inhibitory, or modulatory. So what that means is that some say, do a thing. So the excitatory ones are saying, are activating, are trying to send a thing, a message across. Inhibitory neurotransmitters are trying to stop a message so they can work against one another. Excitatory will say, hey, start trying to do an action potential. Inhibitory ones would be like, no, don't start to do an action potential. So at the molecular level, they are changing if there are gates opening on that neuron to send a message down the action potential. Modulatory ones are just or modulate the message or groups of neurons. So those are the 3 primary jobs that they do. Again, we'll go into more detail on that in psychopharmacology chapters. But here are the main neurotransmitters. You might also notice some of these neurotransmitters are also hormones. So a few of them are hormones and neurotransmitters. There are also hormones that are not neurotransmitters. So there are neurotransmitters that are just neurotransmitters. There are neurotransmitters that are also hormones, and there are hormones that are not neurotransmitters as well. So, for example, dopamine, serotonin, norepinephrine is a really good example of both a neurotransmitter and a hormone. So, epinephrine, hormone, and neurotransmitter. But those are like the main categories. Each of them has variations that build up to that 100 different neurotransmitter types, but it's basically just slightly differently structured molecules, usually with these as a base for the neurotransmitter. So here's a couple examples of the different molecular makeup. If you've taken some chemistry classes and remember it, it's been a little while for me. This will help you see how similar but distinct some of these are. And again, for getting up to that 100, it's basically slight variations on these main 8. All right, so with that, again, Coming back to plasticity, so that capacity for change, this is basically because of that physical process of connecting dendrites and axon terminals to make more synapses, to make more branches, to make a strong network. Another thing that the book doesn't go into too much detail about, but there's a complicated biochemical process that as a certain pathway to do something. Let's say you have a habit of checking your phone when you hear a notification. So you hear it, your hand goes automatically to your pocket or your purse or whatever it is. You pull out your phone to look at it, and you've done that so much, it is now a habit. Well, your neurons actually need less energy to get that message sent because it's part of this common network rather than having, let's say, you normally need 50 hits to that neuron to start the action potential. Maybe now, since it's done it so much, it knows, hey, I only need like 5 hits of other neurons around me in this network to activate and continue on. That's basically what a habit is. And so that's that physical process of the neurons talking to one another, being efficient, using less energy, makes it hard to break habits, but it also makes new habits very strong. It's also part of learning. You are actually learning by making new connections in your brain, using different areas, reviewing things. This is one of the main reasons I say, well, read the book first before coming to lecture. Come to lecture with questions. So now you're getting the material twice, and then review it later. So, and then you're getting it at least 3 times. Maybe the third time is right before the test, but 3 times is much better than 2. 2 is much better than 1. And we'll talk about memory more specifically later on as well. So a key here with brain plasticity is if any kind of disease, damage, injury is too extensive, then the neuron might not be able to regenerate. Any network, if a big area is too damaged, let's say from a stroke or a very bad hit on the head, like a concussion, you might not be able to have enough plasticity to get around that. But when there is plasticity, it usually happens in 3 specific ways. I put up 2 fingers while I did that, but I think it was out of frame actually, so I shouldn't have even mentioned it. So 3 specific ways. One is collateral sprouting. This is when the axons of healthy neurons grow new branches. So there are growing new branches, and these are usually axons that were part of the network. Like let's say 5 neurons were part of this network, 2 of them got damaged. Well, the other 3 can grow new branches and kind of take over that function. So usually this is happening with nearby neurons that are part of the same or similar pathways. So that's collateral sprouting. It's like next to it, sprouting new axon branches, sprouting new dendrite branches. Another is substitution of function. And so this is similar and distinct in a couple ways. So the damaged regions is taken over by other brain areas. So let's say, for example, you completely lost the use of your hands. This would be more likely to happen if you were younger. So terrible accident, you no longer have hands, but you do have feet. You could literally have the area of your brain that is focused on motor control for feet start to take over the control for hands. So that you now maybe got your foot area and your hand area are both now kind of talking to the feet. So that could happen. You've substituted the function. This has happened, we've seen from people that get an injury in the language processing center. We talked about in chapter 2 about how Broca's and Wernicke's area are both here on the left side of the brain, and that's where pretty much all language processing happens. But if you get damage there, especially earlier on in life, your brain can move that to the other side of your brain. So another cool thing that we might get a video on later on is some people, when they go in for some operation or for some headache when they're an adult, there have been people who have gone under an MRI and the MRI scans their brain and they realize, oh, you have only half of a brain. There are people who could be walking around, could be you. You might not know. If you've never had it, I've never had an MRI of my brain, so maybe it could be me. There are people who have half of a brain, but that half of the brain is taking all of the functions that a whole brain. And that is pretty incredible. Just really goes to show how amazing the plasticity is. In that kind of case, obviously that person was born, they developed with half of a brain. And so it always, from birth, it was learning how to do all of the processes, and it varies. Some it's like completely half or all of that. So there's a lot of variations on that because then you've got to have nerves hooked up to that one half of the brain, that kind of thing. But it's pretty neat. The brain is capable of dramatic plasticity, easier the younger you are, but is possible later on in life too. So again, this substitution of function, again, it's usually part of that collateral sprouting. It's happening in the areas that were part of the process. So, and that makes sense. If that neural network, those neurons are working together, even if it's on this side of the brain to this side of the brain that it's connected, it's easier for that part of the network to take on those new functions. Another one is neurogenesis. So neurogenesis is the term for new neurons being created. So in the hippocampus, we do have some stem cells that are some what is it? Human cranium, no, human nervous system stem cells. Like they already know, like, hey, I'm going to become a neuron, but they're still a stem cell. So they're in the hippocampus, in kind of the lower part of the hippocampus, like the bottom part, the SVZ subventricle zone, and we do make some stem cells into new neurons. There's conflicting evidence on if that makes a difference in things like memory or plasticity, but we've seen a lot of dramatic effect in mice when we have them do more neurogenesis. It also looks like in human, the olfactory bulb is doing neurogenesis, but those are the two places concretely. There's a couple other places that there's like conflicting evidence for humans if we're doing neurogenesis, but those are the two places we know for sure. The hard thing here is that most of the research on neurogenesis is done with rats and mice. Rats and mice have a lot more areas of their brains that are doing stem cells neurogenesis all the time. So the stem cells in those areas are able to divide and divide and divide across the whole rat lifespan and then become a neuron. Humans, less so. We do this much less than rats. When it was first discovered, we kind of assumed that humans might have the same amount of neurogenesis, but we have a much lower amount of neurogenesis, which is too bad. But it is a really good positive that we do have any neurogenesis. In the future, we might have a lot of, say, medicines or ways that we can encourage our brains to do more neurogenesis. One finding for rats is that exercise led to more neurogenesis. And we see a lot of positive effects in humans from exercise. Could some of that be neurogenesis? Some scientists suggest yes. Some scientists suggest that it's not clear enough that it's neurogenesis. And the main reason it's hard to figure out neurogenesis in humans are because of the methods of studying human brains. So we're not putting probes into people's brains. We are not genetically modifying people's brains like we do with rats. The only time we put probes and things into brains is if someone's already going into a brain surgery. So there's a lot of limitations on how we can discover this neurogenesis in humans and then try to influence it, alter it, make it better. But it is good that we do have some neurogenesis. Maybe we'll see more advancements with that, or maybe we'll discover a couple of the other areas that are like maybe we'll have a clearer picture in the next few years of those areas having stem cells still dividing and creating new neurons. So this is, I believe, a person talking about this.
Neurogenesis is the production of new neurons in the brain. For a long time, it was believed that the brain didn't produce new neurons after adulthood. But about 10 years ago, there was some evidence that indeed the adult brain does produce new neurons. There were these new neurons in a part of the brain known as the hippocampus. And the hippocampus is a part of the brain that's involved in learning and memory. We know it's necessary, actually, for some aspects of learning and memory. After much discussion about these new neurons and the fact that they happen to be in the hippocampus, we decided to investigate whether or not they might potentially be involved in learning and memory. So over the past 10 years, we've accumulated considerable evidence that they are. That they're certainly affected by learning, there's no doubt about that, and they might even be necessary for some aspects of learning. So the hippocampus has these cells that are somewhat like stem cells, and so they just continuously produce these new cells. So these cells are very, very sensitive to their environment, the external environment as well as kind of the internal environment of the animal, hormones and things like that. However, once these cells are produced, oddly enough, most of them don't survive. What we wanted to know is whether or not if we could keep these cells alive if animals were to learn something new. So what we did was we train animals on these different learning tasks that require the hippocampus, that depend on the hippocampus to do it, right when the cells are about to die. So the cells are generated, and so we mark them with a neurochemical marker that can detect these new cells. And then we can monitor them across this period of time. And then we train animals on these various learning tasks, and we find that the animals that learn this task keep these cells. But if you don't learn the task, the cells die. We use the rat because we know a lot about the hippocampus of the rat, and so we can manipulate these various learning tasks and determine what is it specifically about learning in that model that rescues these cells. And the tasks that we focus on are called associative learning tasks, where an animal learns to associate one stimulus with another stimulus later in time. The task that's really effective is a task known as trace conditioning. And in trace conditioning, the animal hears a tone, and then there's a period of time where there's nothing. And then half a second later or so, he receives a stimulation of his eyelid. And that causes him to blink. It's called eyelid conditioning. And the animal learns that the tone predicts the stimulation and blinks eventually in anticipation of the eyelid stimulation. So it's not the only type of learning that rescues these cells, but that's just the one we've mostly focused on. One other focus of my laboratory has been sex differences, looking at sex differences in learning and how those sex differences affect the brain. When we were trying to determine whether or not it was really learning, that rescues these cells from death, and not just something about the training experience or the stimulation or even the stress of it, we thought, well, maybe it would be interesting to look at sex differences in learning, because we know that under certain conditions, females learn better than males do. And so we thought, well, it would be interesting to see if then, by virtue of the fact that they learn this task so much better, would they rescue more cells than males do? And indeed, that's what we found. I think, that these data that we have in animals and rodent species are maybe suggestive and maybe support this idea that if you continue to learn throughout your life, you are continually changing your brain and potentially keeping neurons there that wouldn't otherwise survive.
So I decided to watch it anyway because it is a good video and fairly short. But yeah, most of those main findings of being able to learn and seeing the neurons stay, those are with rodents. And that's the hard thing, is that we can see the association, we can see that correlation that if humans do a learning task, we see they do better. But what is that? Is that new connections from brain plasticity? Is that these new neurons? So we're still trying to figure out in humans the extent, but it doesn't seem that we have as dramatic of an impact from our new neurons as rats. But the fact that they do exist, that we still do have in a couple areas of our brain, these neural stem cells becoming new, like splitting and then becoming new neurons, is a pretty positive thing for us. It probably has some impacts, even if it's not clear, super clear right now, without more invasive kind of research methods in humans. And it also suggests another piece of the puzzle of why some of the things that we see do work, for whether it's treating mental health conditions, whether it's treating stroke victims. All right, so all of these things. So that is a lot about the brain. Definitely review, just skim over the sections in the book, look over the neuron, maybe try to describe the process to your own friends. These would be really good ways to kind of practice and learn this material and make some new connections in your own brains about neurons. And so definitely check the chapter that's listed in your syllabus to make sure which chapter we're going to be reading next time.